Hi guys, what we're looking at right now is work that's going to help you with resource pack assignments 2 through 4, I believe. And the idea of using polarity to discuss what's going to dissolve and a little furthermore, what's going to be able to conduct electricity once it dissolves. So at the heart of dissolving is this little catchphrase, like dissolves like. And what we're talking about there is ideas of polarity. If something is polar, like water, it's going to be able to dissolve other polar compounds. If it's something that's nonpolar, like hexane, it won't be able to dissolve polar compounds and instead will only be able to mix with other nonpolar compounds. So let's real quick take a look at this diagram that I've got here. On the left is just pure H2O. And we know because of symmetry in the previous video that water is a polar molecule. It only has one line of symmetry. That must mean it has a positive end and a negative end. It's not going to break apart completely, but we do see some difference in charge. And if you look at table S and the electronegativity values of oxygen and hydrogen, what you're going to find is that oxygen has a higher value of electronegativity than hydrogen does. And that means it attracts electrons more strongly than hydrogen does. So what we see is that in water, oxygen acts like it's negatively charged, and hydrogen acts like it's positively charged. So within water molecules alone, what you see are these attractive forces between positive and negative ends of water. And this is actually a very, very strong intermolecular force that we call a hydrogen bond. And remember, a hydrogen bond is a very specific type of intermolecular force that acts between H bonded to either F, O, or N. In the case of water, we've got hydrogen bonded to an oxygen, so this very strong attractive force between molecules is able to take place. This is what makes water boil at a much higher temperature than other compounds of its size. It has the ability to hydrogen bond. If I take this sample of water and I try and dump some table salt into it, so sodium chloride, what's going to happen is that sodium and chlorine will break apart into their positive and negative pieces. And this works really well for water. That makes sodium chloride a very, very polar molecule, so it's going to dissolve in this polar solvent. And what's actually going to happen is water, with its negatively, quote unquote, charged ends, can actually surround the positive sodium ion. And now what we see is, the hydrogen bonds aren't existing necessarily between water molecules in this diagram, but what we do see is this strong attraction between the sodium and the negative ends of the water, the oxygen side. And there's space for the chlorine as well. If you take the positive ends and surround that negative chlorine ion, we see the same sort of attractive forces between positive hydrogens and the negatively charged chlorine. This is why like dissolves like. Polar things will be able to have a negative and positive half, and they'll be able to be attracted to the positive and negative sides of other polar compounds. Were sodium chloride not to have a charge, maybe it's something like hexane, there would be no reason for the water molecules to be attracted to it, so it would not dissolve the substance. That's why when you pour oil, a very nonpolar compound, into water, the two separate out into two distinct layers. The water wants to hang out with itself because it's attracted to itself, and the oil has no business getting all mixed in with the water because there's no positive-negative attraction going on there. What we see when we do dissolve a polar compound, in this case an ionic compound, so superpolar, is that we create a homogeneous mixture because we have spread out those ions uniformly through the solution. And in this particular case, we have also created mobile ions, which is going to equal an electrolyte. We are going to be able to conduct electricity with this particular solution. Not everything you dissolve in water can do this. In order to be an electrolyte, you must be able to break apart into positive and negative mobile ions. So we can see that sodium chloride was easily able to do this. Since it was made of a metal and a nonmetal, the metal automatically took on a positive charge and the nonmetal took on a negative charge, and it was able to split apart when it was put in water. Not all polar substances can do that. And to help you out on what's going to be an electrolyte and what's not, table F is the easiest way to figure out, is something an electrolyte or is it not? In general, there are three types of electrolytes. We've got acids, we've got bases, and we have soluble ionic salts. Typically, we just refer to these as salts, but I think it'll help make using table F a little bit easier to think of it this way. If we look at table F, what we see are two main columns, things that are soluble, that will dissolve, and things that are insoluble or won't dissolve. And they're all based on ions that substances could break apart and form. So if we take the compound NaCl from our diagram, there's really only one way to break apart this compound into a positive half and a negative half, and that's to say sodium's going to be a +1 and chlorine's going to be a -1. Looking on this table, I immediately see Na+. Anything that can be broken apart into an Na+, without exception, will dissolve in water. So automatically, without even checking chlorine, I know that this thing is going to be able to dissolve and become an electrolyte. You could double check on the chlorine, and here it is. And sure enough, in NaCl, the chlorine is not combined with silver, lead, or mercury, so we're still 100% certain on this thing dissolving. You can use this method for any type of ionic salt. So let's say calcium bromide. In this case, it's going to break apart into the metal and nonmetal components. Calcium is going to be a +2, and each bromine is going to be a -1. You're not going to find calcium in either of these two columns, so you're going to have to look for the negative half. And I see bromine right here in the halide position, right where I found chlorine. And sure enough, it's still not combined with silver, lead, or mercury. So this salt, calcium bromide, will be soluble and it will form an electrolytic solution. What's more, if you notice, we've now formed 1, 2, 3 different ions, 1 calcium and 2 bromines. So this is actually going to conduct electricity even better than a saltwater solution, because this guy only formed 2 ions. So the more ions you form when you dissolve in water, the better of an electrolyte you are. Let's take a look at a common acid that's used as an electrolyte example, and that's CH3COOH. If you look on table K on your common acids, you're going to see this listed as acetic acid. It's tempting to want to break this apart because you see the OH right at the end, but if you do that, that leaves CH3CO to be your positive piece. And nowhere on this table or the table right above it, table E, are you going to find CH3CO+. That means that just doesn't happen. So in this case, it breaks apart. I see CH3COO- as a very probable ion to form. And then that would leave the H as an H+, which matches our definition of acid. So that's wonderful. Sure enough, without exception, anything containing this ion will be soluble, so this acid is an electrolyte. And that's going to be true of all acids, hydrochloric acid, anything listed on table K. Same deal with bases. NaOH is a soluble base, and you can prove that to yourself on table F. Any and all bases listed on table L are going to be electrolytes. So check out assignments 2 through 4 and see what you can do with this idea of electrolytes, like dissolves like, and homogeneous solutions, what it means when you dissolve uniformly.